batteries. So batteries are voltaic cells, and they are, of course, extremely useful. So unlike the pictures we've seen when we've been doing calculations, it's not like two beakers connected by a salt bridge with a voltmeter, obviously. So people have found ways to package these voltaic cells into convenient packages, right, that you can stick in your flashlight or have in your phone. And the actual reactions that happen in the battery depend on the type of battery. There's a lot of different ones. Now the good news is I am not going to require you to remember specific reactions from specific batteries because it's stupid. But we just want to get an idea of what batteries are and appreciate how awesome electrochemistry is. So one type of battery is a dry cell. And this is the type of battery that you stick in a flashlight that you have in your cell phone. Dry cell just means that there's not a lot of liquid. If you're familiar with the older car batteries, there are still some that you have to check the water level in, and you have to add water sometimes. That is not a dry cell. I'm not sure if it's called a wet cell, but it's not a dry cell. So dry cells don't contain large amounts of liquid. Here's an example of one. We have a graphite rod, and then there's a moist paste of manganese 2 oxide and ammonium chloride. And then the outside, the case, is made out of zinc, and that acts as the anode. So we've got the anode is the negative terminal where you connect at that end, and the little bump that sticks up here is the graphite rod, and that's the positive terminal. And so this slide apparently is set up for us to write the overall reaction for this, so I guess we should do that. So we've got zinc being oxidized and the manganese being reduced. And they both use 2 electrons. So I really don't remember why I did this, but whatever. So we've got zinc and 2MnO2 and ammonium ions. The electrons cancel out. And then we get manganese 3. Yeah, 2. Solid. And ammonia. And water. So, the reactions chosen here are ones that you can put into a cell, right? You wouldn't be able to do this necessarily with copper ions, right? But these 2 half reactions together give a voltage of about 1.5 volts. And so you can put the batteries together in series to get higher voltages. Any questions?
About the gaseous products from redox reactions, for example, with the ammonia, would it dissolve into whatever available solution would be inside the battery?
Yeah, I believe the ammonia would just dissolve into that moist paste.
Okay.
The quantities are going to be pretty small, yeah. So alkaline batteries, another type of dry cell, but here the half reactions are in basic medium instead of acidic. Right over here, well, it's not exactly obvious that that's acidic, but this is a weak acid. So Here, we've got the same half reactions, right? But the overall equation is a little bit different. The voltage produced is the same. Isn't this guy weird looking? So that's a manganese ion with two different manganese ion with two different anions, an oxide ion and a hydroxide ion. Those are the sorts of things we completely ignored in Chem 1A. So these have pretty much taken over from the standard dry cells because they last longer. They work longer and they last better on the shelf than regular dry cells. You guess what brand that is? Duracell, the copper top, right? Lead acid storage batteries, these are the sort that you'll find in your car. These have 6 different cells that are wired in series so that you get a total of 12 volts because each cell only gives 2 volts. And you can't just make it bigger to get more voltage, right? It has to do with the relationship between the cell potentials of the half reactions. So, but you can put them together and get more voltage. So, here the overall reaction is going to be lead plus lead oxide, that's lead 4 oxide, and 2 hydrogen sulfate ions. And 2 hydrogen ions. And 2 electrons. And that's going to give us 3 lead sulfates and 2 waters. Now, what's really kind of weird about this is we have 2 different oxidation states of lead. We have solid lead at 0 oxidation state, and then we have the lead 4 oxide, so lead 4. And the one's being oxidized and the one's being reduced, and they produce the same product, which is the lead sulfate, so lead 2. So the product here, the lead sulfate, is a solid, and if the battery runs for too long, then that solid coats the electrodes and ruins the battery. These batteries can be recharged. You can run the reactions backward by applying a voltage to the battery, and that's what the alternator in your car does. So the battery is used to get the car started, the internal combustion engine started, and then while you're driving, the engine alternator uses some of the energy from the gasoline that's burning to recharge the battery. So if your alternator is dead, you could get a jump and get your batteries and your engine started, but then wherever you're going, as soon as you turn it off, you're going to need another jump because your battery's still dead. Any questions? And the lead in these is why you're not supposed to just, throw these in the trash, right? California has a lot of rules about that, and they're trying to recycle. Yes?
How is the life of the battery affected when you combine multiple batteries together?
Like if you put 2 of these in series,
Yeah.
I'm not sure if that would affect the life of the battery at all. Yeah. because you're getting the voltage. I think the experience for the individual cell is the same. That would be my guess. Other rechargeable batteries, nickel cadmium or NiCad batteries. These have that name because you've got solid cadmium that gets oxidized, and you have another one of those funky looking ionic compounds with nickel in it that gets reduced to nickel hydroxide. And that gives an overall voltage of 1.3 volts. Again, solid products build up on the electrodes, but you run current through it in the opposite direction, you can regenerate the reactants. One of the problems, which I think a lot of manufacturers have largely solved, one of the problems with recharging batteries is knowing when to stop. Because once you've gone all the way back and you've used up all those products, if you keep applying voltage and running current through it, you can get undesired reactions occurring. And that's where batteries can blow up, right? So most battery chargers now have electronics in them that can sense when the battery is fully charged and will shut it off. And that's really nice. I just found some IKEA rechargeable batteries in my daughter's stuff. I'm like, no wonder we have no batteries. And stuck them in the charger, and I love this little charger. The light comes on, and then it knows when they're done, and the light goes off, and you're like, okay, we'll stick some other ones in here. Back when I was a kid, you had this box that you stuck the batteries in and hoped you remembered. I never had anything explode, but yeah, they didn't work all that well.
I've had things get really close to exploding.
Yeah.
Because when I was a kid, I did like RC racing and
Uh-huh.
things like that. We used lithium batteries, and they would bump up really, really big sometimes.
Yeah, if your battery is bulgy, that means it's not good to use it anymore. And sometimes you come across an old alkaline battery left in a toy or under a bed or something, and it's all crusty and corroded. Yeah, don't try cleaning it up. It's not going to work. And some of that stuff is, could be pretty irritating to your skin. So if you get it on your skin, just wash your hands right away and dispose of the battery. Nickel metal hydride, or NiMH batteries, are becoming more popular because cadmium is very toxic. And so, you put all these nickel cadmium batteries out in the environment, and I think most people are not observing the guidance that you're not supposed to throw batteries in the trash, right? And so then all these nickel cadmium batteries go to the landfills, and then eventually can leach out, and you've got cadmium all over the place.
How are you supposed to discard them then?
Well, see, that's the issue, isn't it? You're supposed to take it to an approved recycling place. Yeah, good luck with that.
Yeah.
Mm-hmm. That and the fluorescent light bulbs.
Does that go
So
for
can we just throw them in a recycling bin?
No, no, you can't. Another advantage that the metal hydride batteries have is that they have greater energy density. And what we mean by energy density is the energy content per unit mass of the battery. So especially if you've got something like a drone or an RC airplane or something, you want that battery to be as light as possible, right? And so the nickel cadmium ones, some of them have no, that's the next one, never mind. Anyway, they're more energy dense. You get more energy. Yeah, I'm just saying the same thing over here. You get the idea. Lithium ion batteries, these are, the new kid on the block. These have even higher energy density. Lithium is, one of the smallest elements. So that plays into its favor. And this is what you're going to see in your cell phone, your laptop, digital camera. These batteries work in a very different way from the electrochemical cells that we've been learning about. And so as your book says, it's just beyond the scope of the course. But basically what happens is that you have lithium ions moving that cause the current. It's kind of crazy to think about. And then there are fuel cells. So a fuel cell is different in that the fuel cell consumes a fuel. The battery is just self-contained, and you can run the charge down and you have to recharge it, but there's nothing you put into a battery to keep it going. A fuel cell, though, is going to consume reactants like hydrogen. So the hydrogen-oxygen fuel cell is the most common. You've got hydrogen gas going past the anode, which gets oxidized, and oxygen gas flowing past the cathode, which gets reduced, and they form water. And this sounds like just a really great thing, right? Because there's no toxic byproducts or anything. You're just making water. The problem is, where do you get the hydrogen? You go down to the hydrogen store. Where do they get it from? Well, you can make hydrogen. Let's see, did we talk about that? No. This is a illustration of the hydrogen cell, hydrogen-oxygen cell. You can make hydrogen from water by passing electric current through it. So now you're passing electric current through water so that you can get electric current from hydrogen and oxygen forming water, right? And then there's the heat tax, right? And I think somebody out there put something up on their door. The laws of thermodynamics. You can't win, you can't break even, and you can't quit the game. It's just stuck, right? So why would this even be a good thing? Well, if you could use, say, hydroelectric, water falling, to create the hydrogen, that's going to have very little impact on the environment. If you can harness the power of sunlight to do that, but that again, you have to make the solar panels, right? And then they don't last forever, and that contributes. It's very, very complicated. The thing about the hydrogen-oxygen fuel cell is hydrogen is very flammable and explosive. Interestingly, oxygen really isn't flammable, but it's required for combustion. So when it's around, lots of other things burn that wouldn't normally burn. So, any questions? Yes?
Would you need to have ions within the water to be able to create an electrical current?
Say that again?
Would you need to have like ions in water to create an electrical current?
Yes. Yeah. So this is an electrolyte solution that does have ions. Yeah. So, people are working on this stuff, and I think eventually someday we're continuously making progress. We'll get there eventually.